Hello friends, in today's question, a highly rigid cubical block A of small mass m and side L is fixed rigidly onto another cubical block B of the same dimension and of low modulus of rigidity nu, such that the lower face of A completely covers the upper face of B. The lower face of B is rigidly held on a horizontal surface. A small force F is applied perpendicular to one of the side faces of A. After the force is withdrawn, block A executes small oscillation, the time period of which is given by. So we are given two blocks, A and B. So let us suppose this is our block B, and on the block B there is a block A which completely covers block B, and this block B is tightly fixed to the surface. So this is a surface, and it is said that A is rigid where B has a slight low modulus of rigidity which is given as nu, and force is being applied perpendicular to the block A which is given by F. Now because of this force, the block A will not change its shape because it is said that it is highly rigid, whereas because of this force F there will be shear stress, or rather we can say shear force acting on block B, because of which it is going to be deformed and the new shape will be coming something like this. So this was our initially block B, and because of the force which is being applied, this is the new block B, and block A will be as it is above block B. So this is block A, this is block B, and we have B applied a force F, and we can say this is angle theta, and this is x, by which the block B moves from its original position, and it is given that the side is L. So this we can divide into two parts. Now in order to solve this particular question, we can approach it into two different ways. In the first part, we can use the concept of, you can say, effective spring constant, which will be dependent upon the modulus of rigidity as well as block length. And the second way to solve the same numerical is by using the traditional method of finding out the you can say modulus of rigidity, in which we take angle theta, and based on your sine of theta we find out L upon x, then we say theta is small, so theta is equal to L upon x, and something like that. So first of all, let's try to the you can say in the first method. So first method, so we can say that oscillations are due to the shear oscillations are due to shear deformation of block B, deformation of block B, and this block B is going to behave like a spring, which behaves like a spring in response to the force F applied on block A. Now the shear modulus of block B, which is given as nu, is going to determine the restoring force. You can see the shear modulus nu of block B determines the restoring force. Determines the restoring force. And once the force, applied force, is withdrawn, the block A, or we can say once the applied force on block A is withdrawn due to restoring force caused by the elastic deformation of block B, there will be some kind of oscillation. We can say once force F is withdrawn, block A oscillates. Block A oscillates due to restoring force caused by the elastic deformation of block B. Due to restoring force caused by the elastic deformation of block B. So we can treat that block B is acting some kind of a spring. So therefore, let's find out what will be the effective spring constant for that block B. So you can see effective spring constant. So we have a block of length L and shear modulus nu. So it is given that for block B, length is given as L, shear modulus is given as nu, and the spring constant, let us suppose, or rather we can say the effective spring constant is K. If effective spring constant is given as K, so therefore this effective spring constant will be proportional to the cross-sectional area. So if the spring constant is equal to K, then K is directly proportional to cross-sectional area, which will be equal to nothing but L square, because it is given as cubical, and it will be inversely proportional to the you can say length of the block, inversely proportional to length of block, which is given as L, and it will be, sorry, here I missed, directly proportional, and it also directly proportional to shear modulus, directly proportional to nu. Therefore we can write that K will be equal to nu area of cross section divided by length, and length goes by length, so we get that spring constant will be equal to nu multiplied by length. So we found out the value of the spring constant, and from here we can find out directly the time period of oscillation, because we know that the time period of oscillation, which is given as t, is equal to 2 pi mass divided by spring constant. We found out the spring constant, so we substitute here, where t is equal to 2 pi square root of m divided by nu L. So this is the time period. This is the time period of oscillation when force is withdrawn. Now, from the options available to us, we can say that option number D is the correct option. Okay, you can say option D is correct. Now let us try the second method, in which we are going to use more traditional approach. Okay. Second method, we know that modulus of rigidity nu is dependent upon the applied force F, area of cross section, as well as the theta by which the body is deformed. Okay, so we can say the modulus of rigidity nu, modulus of rigidity nu is equal to F A theta. Let us call the equation 1, where F is the shearing force or applied force. So F is our shearing force, A is our area on which the shearing force is applied, area on which shearing force is applied, and theta is our angle. Theta is the angle by which the surface of the object, is displaced from the original position. Surface of the object is displaced from original position. Okay. So this was our original position, and when force F is being applied, it is being deformed by an angle of theta. So theta is the angle by which the body is being deformed. So as the body is given as cubical, so we can say that area of the cube, which is A, is equal to L square. and we can use, you can say, law of motion. We can say the net force that is being applied, if is given as F net, then that will be equal to mass into acceleration. So you can say according to Newton's laws of motion, F net is equal to mass into acceleration. Let us call this equation 2, and the time period, the standard formula is given as time period of oscillation is given as T, which is about 2 pi L upon G. Let us call this equation number 3. So let me redraw this figure again here, so that this is surface, original position, and it is being sheared by applied force, something like this. This is angle theta, and we have this as our x. A is our fixed body, this is A, this is B, and we are given L is its side. So we can say sine of theta will be equal to x upon L, and if theta is very small, then we can say that our theta is equal to x upon L. Therefore, we use equation 1 and substitute value of theta. You can say from equation 1 we get nu is equal to F upon A multiplied by x upon L, and we get F, area is our L square, multiplied by x upon L. This L and L cancels out, so we get our N is equal to F upon Lx. Now from here we can say our F is equal to nu Lx. So this is the value of the applied force. Now from equation 2 we can say that our acceleration from equation 2, acceleration is equal to net force divided by mass, and in this case the net force is given as F, so it becomes F upon m, and we substitute value of F in this equation, we get A is equal to nu Lx upon mass m. And in the equation of the time period, that is from equation 3, from equation 3 our length is equal to x and g is equal to a. We substitute, we get t, a is equal to 2 pi x upon a. Now we substitute value of x, sorry, a, we get 2 pi x upon n Lx upon m. So here x and x cancels out, so we get t is equal to, time period is equal to 2 pi square root of m upon L, nu L, sorry. So answer is coming same. Now this can be also further modified, that suppose if there are 3 blocks and of which the top one is A, middle one is B, and the lower one is C, and B and C are having their modulus of rigidity. Suppose nu B and nu C, and A is rigid. So in this case also we are going to find out, you can say, nu effective, which will be equal to 1 upon nu A plus, sorry, not nu A, but 1 upon nu B plus 1 upon nu C. Okay. So this question can be repeated in n number of times. So you can say that, let me take a new page, that if there are 3 blocks for 3 blocks, we have something like this. This is A, this is B, and this is C, and we assume that A is rigid, B is mild rigid, moderated rigid, and C is the, you can say, least rigid. And for B we have nu 1, and for C we have nu 2, and force is being applied on, once again, on block A. So this way the force is being applied, which is also given as F. So you can modify this figure as, it will be something like this. This is the original positions, and because of the force applied, this is block C. Because it is the least rigid, so it will be tilted more as compared to block B, and block A will be the least one. Okay, so this is A, B, and C. Force is being applied on F. So we have, this is nu 1 and this is nu 2. So therefore we can say that nu effective will be equal to 1 upon nu 1 plus nu 2, and we can find out that period of oscillation for TA will be equal to 2 pi square root of m. This will be now nu effective multiplied by L, okay, because the oscillation is only because of B and C, not because of A. Okay. From here we can say that oscillation depends only on block B and block C, because they have the tendency to be flexible. And this is if the force is being applied on block A. This is the first part. Now we say the force is being applied on block B. Force is applied on block B. So in the shorter term we can say block A, there will be no deformation. And block C, B and C will be having deformation. Block B and C, there will be deformation. It meaning the shearing force will be only affecting block B and block C. So once again, only block B and C will be contributing to the restoring force. Block B and C will contribute to restoring force. Therefore, in this case also, TB will be equal to 2 pi m upon N effective and L. So N effective will be once again given by the same formula. Okay. We can say nu effective will be equal to 1 upon nu1 plus 1 upon nu2. And if the force is being applied now on block C, force is applied on block C. So here also block A, there will be no deformation. Block B, there will be only mild deformation. Block B, we can say mild deformation. And block C, or in the shorter form we can say no deformation. And for block C, there will be deformation. Block C, we are going to have deformation. Therefore, now the restoring force will be only because of block C. Restoring force will be only because of block C. Therefore, the time period of the oscillation will be only dependent upon the modulus of rigidity for block C, that is nu2 upon L. So from here we can make one of the conclusion that the period of oscillation is only dependent upon the bodies or blocks which contribute to the restoring force. Like when the force is being applied on A, block B and block C contribute to the restoring force. So therefore nu effective is 1 upon nu1 plus 1 upon nu2. When force is being applied on block B, there is no deformation in block A, and one second deformation is in block B and C. So both contribute to restoring force. Therefore the time period of oscillation will be same as of block A. Whereas when the force is being applied on block C, block B will be mild deformation. So we can assume that it is close to no deformation. So entire period of oscillation will be dependent upon the modulus of rigidity for block C, which is nu2. So this completes the question. Thank you.